Good evening, everyone. So, recall that in the last class we discussed system comparison theorem, which says that there are two equations y double dash plus q of x y is equal to 0, z double dash plus r of x z is equal to 0, and if q is greater than r, then y of x vanishes at least once between successive zeros of z of x. Now, we will discuss the next question, which is based on the system comparison theorem, which says that let y be a non-trivial solution of Bessel equation on the positive x-axis. Using system comparison theorem, we will discuss three cases when p is from 0 to half, p is equal to half, and p is greater than half. So when p is less than half, we need to show every interval of length pi contains at least one zero of ypx. So first recall where you have seen the Bessel equation. So in section 24, we found the normal form of the Bessel equation, because for the normal form only we can use the system comparison theorem. So this is how the normal form looks like. Yes, the next thing is we have seen in section 24 that when p is less than half, then h of x is positive. So it is greater than 1. So h of x is greater than 1. For system comparison theorem, I need one more equation, and here it is clearly visible h of x is greater than 1. It means I could have the other equation z double dash plus r of x z is equal to 0, where r of x is equal to 1. So that's why I choose the other equation as z double dash plus z is equal to 0. Now I need to show every interval of length pi contains at least one zero of ypx. Yes. So now from the system comparison theorem, u of x vanishes at least once between successive zeros of z of x, and the z of x has solutions as sin x minus x naught and cos x minus x naught, which vanishes over an interval of length pi, or we can say that the distance between the successive zeros of zx is always pi. It means that over an interval of length pi, y of ypx vanishes at least once. So using system comparison theorem, ypx vanishes at least once between successive zeros of sin x cos x, and zeros of sin x cos x differ by pi. So that gives us the required answer. P is equal to half, we need to prove distance between successive zeros of ypx is exactly pi. This is straightforward. If you try to put p is equal to half in h of x, then h of x becomes 1. So it means I have the equation u double dash plus u is equal to 0, and I know that for this equation the successive zeros or distance between successive zeros is pi, because they are sine cosine function. So for each non-trivial solution, the distance between successive zeros is pi. This is little bit tricky, which says if p is greater than half, then every interval of length pi contains at most one zero of ypx, at most one. Now again, if you go back to section 24, then for p greater than half, h of x is less than 1. So h of x is less than 1, it means I can introduce the next equation same as z double dash plus z is equal to 0, but I need q of x. So here q of x is 1 and it is greater than h of x. That's why I called z double dash plus z as first equation. Yes. So now from the system comparison theorem, z of x vanishes at least once between the successive zeros of equation 2. Yes. So I will consider the three cases because I have to show at most once. So why, in what condition we will have no zeros, in what condition I have 1 0, and under what condition I have, why not two zeros or more than one zeros. So if you see this one, then the first case is straightforward. I am just assuming for sin x, but can be proved for sin x minus x naught or cos x minus x naught. So for sin x, between any two successive zeros of zx vanishes between two successive zeros of equation 2. So if successive zeros are yp1, yp2, then z of x vanishes. Let's say it is vanishing only once. So in that case, you can see that there is an interval of length pi and yp2 is vanishing once between over an interval of length pi. But if sin x or sin x minus x naught cos x minus x naught vanishes twice between the interval between two successive zeros yp1 and yp2, then you find the interval of length pi where there is no zero of equation 2. So that's why there are two cases, either 1 0 or no 0. But why not two zeros? So let's assume that there is an interval of length pi k and pi plus k, and yp is vanishing twice over that interval. If it is vanishing twice, then I am assuming ux to be sin x minus k, which shows that k and pi plus k are the zeros of u of x. Yes, and between two zeros, yp1 and yp2 are vanishing. I start by contradiction. But from Sturm comparison theorem, now u of x must vanishes between yp1 and yp2. Now what will happen if it vanishes between yp1 and yp2? If it is vanishing between yp1 and yp2, then the problem is that the distance between two successive zeros of u of x would be less than pi, which is a contradiction, because distance between successive zeros of u of x is pi. That's why it is not possible. So very interesting question. Let's move to the next question. Consider the differential equation u double dash plus q of x u is equal to 0 with q of x is greater than equal to m square. Using Sturm comparison theorem, we need to show every non-trivial solution has infinitely many zeros, and distance between two consecutive zeros is at most pi by m. First part is very simple. Please do try by yourself. So you need to introduce one more equation. One is already given. Hint is given, q of x is greater than equal to m square. It means the other equation is z double dash plus m square z is equal to 0, which have periodic solutions as periodic functions which have infinitely many zeros. That's why u double dash plus q of x u has infinitely many zeros. So this one is straightforward. I assume this equation. The problem comes when I have to show distance between two consecutive zeros is at most pi by m. Now first observation is distance between two zero is pi by m does not mean that any interval of length pi by m contains at least one zero, because you may try to prove this one, which is not correct. You can see the example: pi by m, 2 pi by m, 3 pi by m. If one zero is 1.1 pi by m, the other is 2.9 pi by m, their distance is greater than pi by m. Yes, so distance between two zeros is pi by m has nothing to do with to show that interval of length pi by m contains at least one zero. Now how do we prove it? So we will use the same approach which we have used to show p is greater than half. So if you see that approach, then what I will do is that I will take u of a is equal to 0, because there must be some point a where u of a is 0. Now I need to show that u of x has a 0 in this interval. A is any arbitrary point. If I manage to show this, it means that the distance between the successive zeros, so this is what it means, distance between two successive zeros is at most pi by m, because it is vanishing at a, and if it is vanishing between a and a plus pi by m, then the distance between successive zeros would be always less than pi by m. Yes. Now if this is the second equation, then its solution can be written in this form: sin mx minus ma. Ma is any constant. Now, if you see that approach, then what I will do is that I will take u of a is equal to 0, because there must be some point a where u of a is 0. Now I need to show that u of x has a 0 in this interval. A is any arbitrary point. If I manage to show this, it means that the distance between the successive zeros, so this is what it means, distance between two successive zeros is at most pi by m, because it is vanishing at a, and if it is vanishing between a and a plus pi by m, then the distance between successive zeros would be always less than pi by m. Yes. Now if this is the second equation, then its solution can be written in this form: sin mx minus ma Important observation is that at these endpoints a and a plus pi by m, v of x is 0. So v of a has zeros at a and a plus pi by m. Yes. Now using this term comparison theorem, there is at least one zero of u of x in this interval. This is what need to be proved. So because these are equation 1 and 2, so u of x has at least one zero between two successive zeros of v of x, and we say that a and a plus pi by m are two successive zeros of v of x. So therefore u of x must vanishes between these two successive zeros of v of x, and this is what need to be proved, and that's why the distance would be at most pi by m. So this is the last question, which says that for the given differential equation, which of the following option is true? Please think over it. It's a MCQ. It means you cannot spend more than 3 minutes to solve it, and it's straightforward. So the only thing to observe here is that it is a Bessel equation where p is equal to under root 1 by 256, or which is 1 by 16, which is less than half. So when p is less than half, then every interval of length pi contains at least one zero of y of x. So this we have already proved. So that's all from this chapter. In the next class, we will start a new chapter.